In section 12.4, we look at the normal distribution. In 1 million BC, the mean height for men was 4 feet 6 inches. The mean height for women was 4 feet 2 inches. Because of improved diet and medical care, the mean height for men is now 5 feet 10 inches, and for women it is 5 feet 5 inches. Mean adult heights are expected to plateau by 2050. So let's suppose that a researcher selects a random sample of 100 adult men, measures their heights, and constructs a histogram for the data. The graphs illustrate what happens as the sample size increases. And so in the first figure, you can see what the sample looks like of 100 men. If we were to increase the amount of men that were asked or measured, you can see what it would look like in figure B. Again, for figure C, we're increasing the sample size, which will lead us to what the normal distribution of a population should look like in figure D. So in graph C, if you were to fold the graph down the middle, the left side would fit the right side. As we move out from the middle, the heights of the bars are the same to the left and the right. Such a histogram is called symmetric. As the sample size increases, so does the graph's symmetry. If it were possible to measure the heights of all adult males, the entire population, the histogram would approach what is called the normal distribution. This is what is shown in graph D. This distribution is also called the bell curve or the Gaussian distribution. Graph D illustrates that the normal distribution is bell-shaped and symmetric about a vertical line through its center. Furthermore, the mean, median, and mode of a normal distribution are all equal, and it's located at the center of the distribution. The shape of the normal distribution depends on the mean and the standard deviation. The graph above illustrates 3 normal distributions with the same mean, but different standard deviations. As the standard deviation increases, the distribution becomes more dispersed or spread out, but it still has that symmetric bell shape. In these distributions, the data items tend to cluster around the mean. The more an item differs from the mean, the less likely it is to occur. And so the standard deviation plays a crucial role in the normal distribution by the 68, 95, 99.7 rule. And so that says that approximately 68% of the data falls within 1 standard deviation of the mean in both directions. Approximately 95% of the data falls within 2 standard deviations of the mean in both directions. And approximately 99.7% of the data falls within 3 standard deviations of the mean in both directions. You can see what this looks like in the graph below. So this pink-ish region is where the 68% occurs, and that's between -1 and 1 standard deviations. And then the blue plus the pinkish area is the 95% and the 2 standard deviations. And then tacking on the green area with the blue and the pink gives us 99.7% of our data items. So example 1, male adult heights in North America are approximately normally distributed with a mean of 70 inches and a standard deviation of 4 inches. Find the height that is 2 standard deviations above the mean and 3 standard deviations below the mean. So what we do is we take the mean, which in this case was 70 inches, and then because it's above the mean, we're going to add to it. It's 2 standard deviations, and so you're going to do 2 times whatever the standard deviation is, which was 4 in this case. So this gives me 70 plus 8, and so that means that 78 inches is 2 standard deviations above the mean. The same idea applies for 3 standard deviations below the mean. So you're still going to take the 70, but because it's below, we're going to subtract. There are 3 standard deviations, and my standard deviation is still 4. So that's 70 minus 12, which gives me 58 inches. Let's use the distribution of male adult heights to find the percentage of men in North America with heights between 66 inches and 74 inches, between 70 and 74, and above 78. So using the same information we just had, that means my mean was 70 inches. And my standard deviation was 4 inches. That's from example number 1. So what we want to do is we want to see where 66 would fall. That means this is the mean minus 1 standard deviation. That's 70 minus 1 times 4. Which is 66, and that's what we were looking for. And then we need to check above the mean in the same fashion. So mean plus 1 standard deviation, that's 70 plus 1 times 4, which is 74. And because this is 1 standard deviation above and below, that is the 68% part of our rule. Let's try between 70 and 74. So we already found between 70 and 74 was 1 standard deviation. But heights between 66 and 70, which is what we found in the first part, is the same as 70 and 74. And we know that 68% of our data falls between 66 and 74. And so what we're going to do is we're going to take our 68 divided by 2, and we get 34% because we only want half of that. And above 78 inches. So if we're looking at the graph in the right hand side, we can see 78. Anything above it falls in the green area, which is more than 2 standard deviations from the mean. And so that is when 95% of the data falls between 2 standard deviations. And so that means if it's outside of my 2 standard deviations, the entire graph is 100%, and we're subtracting off the 95%. And so that means there is 5% in the regions that are outside of this area. But we're only looking at half of it. So what we're going to do is we take the 5% and we divide it by 2, and so that gives me 2.5%. Because the normal distribution of male adult heights in North America has a mean of 70 inches and a standard deviation of 4 inches, a height of 78 inches lies 2 standard deviations above the mean. In a normal distribution, a z-score describes how many standard deviations a particular data item lies above or below the mean. Thus, the z-score for the data item 78 is 2. So a z-score describes how many standard deviations a data in a normal distribution lies above or below the mean. And so we can find it by using the data item minus the mean divided by the standard deviation. Data items above the mean have positive z-scores, and data items below the mean have negative z-scores. The z-score for the mean is 0. So the mean weight of newborn infants is 7 pounds, and the standard deviation is 0.8 pound. The weights of newborn infants are normally distributed. We want to find the z-score for the weight of 9 pounds, 7 pounds, and 6 pounds. And so the way we usually denote this is we write z and then in a tiny little number next to it, the data item we're looking at, which is 9 in this case. And so we take the data item, 9, minus the mean, which was 7, and we divide by the standard deviation, which was 0.8. And so this gives you 2 divided by 0.8, which is 2.5. Let's do the same thing for 7. So we take 7 minus 7 over 0.8. Well, that's 0 divided by 0.8, or 0. Same thing for 6. That's 6 minus 7 divided by 0.8, or negative 1 divided by 0.8, and you get negative 1.25. So in the first scenario, this means that 9 pounds is 2.5 standard deviations above the mean. Seven pounds mean that it was, because we got a z-score of 0, this was 7 pounds is right at the mean. And then 6 pounds is 1.25 standard deviations below the mean. Since it was a negative 1.25. So example number 4, a student scores 70 on an arithmetic test and 66 on a vocabulary test. The scores for both tests are normally distributed. The arithmetic test has a mean of 60 and a standard deviation of 20. The vocabulary test has a mean of 60 and a standard deviation of 2. On which test did the student have a better score? So we need to compute their z-scores. So for arithmetic, we're looking at the z-score of 70. And so that's 70 minus the mean on the arithmetic was a 60. And the standard deviation was 20. And so that gives me 10 over 20, which is 0.5. And we're going to do the same thing for the vocab test. We're looking at a Z-score of 66. And so we take 66 minus the mean on the vocab test, which was 60. And then divide by the standard deviation, which was 2. And so this gives me 6 over 2, which is 3. And so because the Z-score on the vocab test was bigger, that means they scored better on this exam in comparison to the other scores. The Z-score measures a data item's position in a normal distribution. Another measure of a data item's position is its percentile. Percentiles are often associated with scores on standardized tests. If a score is in the 45th percentile, this means that 45% of the scores are less than this score. And so the n% of the items in a distribution are less than a particular data item. We say that the data item is in the nth percentile of the distribution. So the cutoff IQ score for the Mensa membership is 132.8, is in the 98th percentile. What does this mean? This means that 98% of the scores fall below that cutoff score of 132.8. Three commonly encountered percentiles are the quartiles, and quartiles divide data sets into 4 equal parts. The 25th percentile is the first quartile, where 25% of the data falls below the first quartile. The 50th percentile is the second quartile, where 50% of the data falls below the second quartile. So the second quartile is equivalent to the median. And then the 75th percentile is the third quartile, where 75% of the data falls below the third quartile. And you can see this in the image below. So statisticians use properties of the normal distribution to estimate the probability that a result obtained from a single sample reflects what is truly happening in the population. If you look at the results of a poll, like the one shown below, you will observe that a margin of error is reported. Surveys and opinion polls often give a margin of error. And so if a statistic is obtained from a random sample of size n, there is a 95% probability that it lies within 1 over the square root of n times 100% of the true population percent, where plus or minus 1 over the square root of n times 100% is called the margin of error. And so example 6, the table shows that in a random sample of 1,000 U.S. adults, 46% of those questioned said that they dread public speaking. We want to verify the margin of error that was given for this survey. And so n in this case is 1,000, because we asked 1,000 people. And so we're going to plug it into the formula that was given above. Plus or minus 1 over the square root of n times 100%. Well, that's plus or minus 1 over the square root of 1,000 times 100%. That's approximately plus or minus 0.032 times 100%. And all we do is we move the decimal place 2 spots to the right, And so that's about plus or minus 3.2%. So let's write a statement about the percentage of adults in the U.S. population who dread public speaking. So we know that from above, there is a 95% probability that the true population percentage lies between So we're going to take that 46% that was reported, and we're going to subtract the 3.2% we found from Part A, which gives me 42.8%. And then we're going to add 3.2% to it. So 46% plus 3.2% gives me 49.2%. So this means we can be 95% confident that between 42.8% and 49.2% of adults dread public speaking. And then we have other kinds of distributions. So although the normal distribution is the most important of all the distributions in terms of analyzing data, not all data can be approximated by this symmetric distribution with its mean, median, and mode all having the same value. So the distribution in the graph below is called a skewed distribution. A distribution of data is skewed if a large number of data items are piled up at one end or the other with a tail at the opposite end. So you can see this in the image below. In this distribution, the tail is to the right. Such a distribution is said to be skewed to the right. The distribution in the graph below has more data items at the high end of the scale than at the low end. And so the tail of this distribution is to the left, and the distribution is said to be skewed to the left.